Today in my video, I'm going to be talking about the Curtius rearrangement and the Hoffman rearrangement. What is a Curtius rearrangement? So a Curtius rearrangement is a thermal decomposition or pyrolysis of isoazides to the corresponding isocyanates. So this is an isoazide. And with heat and N2 minus, this will form into the isocyanate. How does it work? This reaction can be catalyzed by both protic and Lewis acids. It also has a lower decomposition temperature when compared to the uncatalyzed reaction. The synthesis of isocyanate. So we start off with a carboxylic acid. This OH reacts with this halogen. In this case, this is a chlorine. So um, it's going to switch the alcohol group for the chlorine. And then since chlorine is a good leaving group, you're going to use NaN3 to substitute the chlorine for the N3, which forms the isoazide that's needed to form the isocyanate over here. The mechanism of the isocyanate. So nitrogen intermediates right here is what a nitrogen intermediate is, are formed in the pyrolysis of most alkoazides, aroazides, sulfonoazides, and azetoformates. But in thermal conditions, the Curtius rearrangement is different in the fact that under thermal conditions is most likely a concerted process, which means this all happens at once and doesn't form these intermediates right here. And so what happens is the nitrogen's lone pair will form this double bond to this plus charged carbon. And what happens is this OH minus will come and depronate the nitrogen to stabilize it. And this is how you will get your isocyanate. The mechanism of the Curtius rearrangement. And so the first step of the mechanism is the formation of an N-halogen substituted amide. Next, the N-haloamide is depronated and turns into an unstable alkali salt, and then quickly undergoes a concerted rearrangement to the isocyanate via bridged ion. So the water will attack the carbon. This bond will break. The lone pairs on the nitrogen will then attack the water's proton and steal one of them, and then the nitrogen lone pair again will attack this alcohol's hydrogen over here, which forms NH2R plus and pretty much CO2 minus. And then what will happen is that the minus charge on the oxygen, the lone pairs will form a double bond, creating carbon dioxide and the NH2R. Next is the Hoffman rearrangement. So, what is the Hoffman rearrangement? The Hoffman rearrangement is a chemical reaction where a primary carboxamide is converted to a primary amine with the loss of one carbon atom as carbon dioxide. And so you can see this right here. You'll form your isocyanate right here, and then with water, um, this will break and form CO2 and your amine. How does it work? So it works by treating the amide with a halogen like Br2 or CO2 and a strong base like NaOH. Then the reaction goes through an N-haloamide intermediate, which rearranges into an isocyanate. The unstable isocyanate reacts with water to give a carbamic acid, which then decomposes into a primary amine and carbon dioxide. And so the nitrogen's lone pair will attack this carbon. This carbon will break this bond to the nitrogen, and so this looks familiar to the Curtius, where the nitrogen's lone pair will attack this hydrogen right here and steal it and form NH over here. And this then stabilizes. Instead of NH2R, it's just NHR over here. The synthesis of Hoffman rearrangement. So first you're going to start off with a carboxamide, um, NaBrO2 and water, and then heat. This forms the isocyanate right here. Then using water, this forms the unstable kind of intermediate, which will react with itself to, of course, form CO2, and then this over here, which is the NH2. So the key features of this rearrangement is converts amides to amines with one fewer carbon atom, involves halogenation and a base, proceeds through an isocyanate intermediate, maintains stereochemistry of the migrating group, and uses and used in preparing amines for carboxylic acid derivatives. The similarity and differences of both reactions. So the similarities are both reactions are prepared from acyl halides through an addition elimination. Both have important isocyanate steps. Both work best under thermal conditions. The Curtius rearrangement, if I'm not mistaken, has a photochemical mechanism, but that mechanism forms that nitrine intermediate that you don't want. The differences is the Hoffman rearrangement occurs with an amide, the Curtius rearrangement occurs with an acyl azide, and the Hoffman rearrangement needs to be treated with a halide, for a leaving group, while the Curtius rearrangement doesn't. And so the concept questions here